Yeah, hi, so my name is Kobi Hasharoni. I'm from DustPhotonics, and I'll talk about some advances in optical packaging for the design of data center transceivers. A few words about Dust. We were founded 3.5 years ago in 2017, R&D and operations in Israel, production in Thailand, and about more than 100 employees by now. So our market and products are diverse. We are active with both in multi-mode and single-mode transceivers and integrated optics. So we have a portfolio of multi-mode engines, the transceivers from 100 through 4 and 800. And we recently added single-mode transceivers, both based on EML, and we're working also on silicon photonics. In conjunction to that, we are very active in co-packaging, which with silicon photonics will take us to the next generation. Now, regarding the data center network, which is the focus of this conference, we are all familiar with these graphs from Cisco. They are showing the almost exponential increase in the data center traffic throughout the years. And it's no news that this growth is due to the activity in social media, big data analytics, artificial intelligence, internet searches, etc., etc. And as Benjamin showed a few talks ago, the size of those data centers is actually increasing quite significantly. So the data center network could be segmented into three rather large groups. The first one is the cloud applications, the Googles, the Amazons, we know them all. Then we have the high performance computing like Dell and Cray and Fujitsu. And last but not least, the enterprise networks, which is more of the classical telecom, like Deutsche Telekom, British Telecom, etc., or any campus application. Regardless of this market segmentation, all of these are actually different versions of the same data center. And the data center can be realized in this very well-known leaf and spine architecture, where the traffic is actually flowing, I hope you can see my mouse, not up and down, north-south like it used to be, but it's actually flowing between the server racks. And the data center is actually the topology, the full mesh topology, meaning that each server is actually connected via optical interconnects to all other servers in the data center. So the core of the data center is actually the network which connects all of those servers. And those the connection is actually carried out by Ethernet switches, Broadcom, Cisco, Juniper, etc. And these handle the data center itself. Now, those switches are not endless, the capacity is actually limited. And whenever the switching capacity has reached a limit, meaning usually in terms of the radix, so the number of I/O ports, we need to add another layer of switches, another spine layer actually, and therefore the data center grows more and more. So the main feature, the performance of the data center is actually limited by the performance of those Ethernet switches and the optical interconnects or transceivers, which actually connect them to each other. Now, looking at this correspondence between the growth of Ethernet switches and transceivers, we see a very good correspondence between the bandwidth of those switches. Today, we are deploying switches with the bandwidth of 12.8 terabit. 25 terabit switches are actually already being tested in the labs and are going to be deployed probably the coming year. And we can see that the Ethernet, the transceiver speed actually follows more or less the same trend as the Ethernet switches. And on the table on the left, you can see that the correspondence is actually based on the SerDes speed. Whatever SerDes speed is found on the switch I/O ports is actually found also on the transceiver itself. And this is the reason why the transceiver industry has been growing in a very fast rate. And you can see on the graph that the spacing between increased line rates is actually getting shorter and shorter as we proceed in time, because of the very fast increase in the SerDes, electrical SerDes line rate. So at the moment, we have 12.8 terabit switches in the market, and 400G transceivers are deployed. Very soon, we'll have 25 terabit switches and 51, which will actually employ 400 and 800G transceivers. And this is the reason why projects such as MASSTART and others are active, because we must find technologies to actually enable higher bandwidth transceivers to support those switches. There's always an argument or debate whether we should go to multi-mode or single mode, and we see here on the upper left a nice study by Corning from a couple of years ago, which actually showed pretty nicely that more than 60% of all links in a data center are actually way below 100 meters. And at those short distances, actually does not make too much sense to use single mode connectivity, although some players are actually doing it. But the outcome of those studies shows that there's room for both single mode and multi-mode transceivers, and basically they will stabilize in a couple of years, like 60% single mode transceivers and 40% multi-mode transceivers. Regardless of these, both multi-mode and single mode transceivers must be able to support the next generation line rate of 112 gigabit per second. And in 2 or 3 years, we will begin to hear about 224 gigabit per second, and those transceivers will have to support this as well. The device capacity of next generation transceivers is 800 and 1.6 terabit per second, and of course, and again, this is one of the goals of this project. Another thing is that those transceivers should support, multi-mode transceivers should be able to support longer reaches, like 300 meters. While single-mode transceivers support all the way up to 2,000, probably even more in the data center. And then we need to develop technologies which will enable integration with electronics for future co-package efforts. Now, looking at the metrics in which we test our data center transceivers, there are 3 metrics. The most important one is the cost. Actually, the hyperscale players, don't really care too much about performance as long as the cost is low enough. And there's a constant pressure to reduce the cost. You can see some typical graphs here. There's an industry-wide goal of obtaining $1 per gigabit, which is pretty difficult to achieve, especially in single mode. It's doable in multi-mode, of course, but this pressure is continuous. And this requirement, which is very strict, is actually driving the technology very fast, because we must always continuously find technologies which will actually enable lower cost assembly and devices. The next demand is to reduce the power. Now we can see here on the right, on the image in the center, we can see the distribution of power, the segmentation of powers in the data center, and of course we can see that most of the power is actually in the servers, and the transceivers are actually this very narrow red line here. So one might argue, why the hell do we bother about reducing the power of transceivers if they are less than 2%, I think even below that in the data center? That is correct, of course, but the answer is that within a single rack in the data center, and a rack has about 24 to 32 servers and a top-of-rack switch, the allocated power to the rack is actually very limited, most of it going to the servers and to the switches, and therefore the 32 or 64 transceivers that are placed in the switch must actually remain at lower power in order not to exceed the rack supplies. Last but not least, there's a constant demand for higher reliability. You can see here an image from a data center, I don't know which one. The number of transceivers can actually be in the hundreds of thousands, sometimes even a million. And if the operators need to go and fish out a malfunctioning transceiver, this is a very costly and time-consuming process, and therefore reliability, especially for the lasers, but also for the assembly process, is a must, because you must minimize the time spent on maintenance. So all of these requirements lead us to transceiver design, and basically we need to optimize cost, power, and reliability, and therefore we need to design for high volume manufacturing, either fully passive like we do here for multi-mode transceivers, or fully automated as we do here for the silicon photonics in MASSTART. We must design for reduced BOM, minimize the amount of labor-intensive steps to minimize the COGS, and the same design must be able to support several versions of the transceivers, because it doesn't make really sense to design a new transceiver, a new optics for each task in the data center. So here I'm drawing, sketching three transceiver designs. The top one is a multi-mode VCSEL-based transceiver. Then in the middle we have an EML-based single-mode transceiver, and below we have a silicon photonics-based transceiver. We can very easily see that the optical packaging tasks are very similar. Basically, it's all about coupling the light from the laser into the fiber and from the fiber to the photodiode. Of course, with the multi-mode transceiver, the task is actually easier because of the fiber cores dimension. But overall, the technology is more or less the same. These are the optical packaging tasks and challenges that we are actually facing: coupling laser light into the fiber or into the silicon photonics peak in our case, and coupling the fiber light to the fiber and from the fiber to the receive modules. Regarding next generation transceiver, on the right-hand side, we can see some graphs from light counting showing the rise and fall of various transceivers according to the line rate. And I allowed myself to add also my estimated curve for the 800G transceivers, which we don't have, of course, any information about. And we can see that the time difference, the gap between transceiver classes is getting shorter and shorter, because again, the Ethernet switches line rate and bandwidth is increasing at an extremely fast rate. 12.8 terabit is being deployed, and 25 is actually becoming ready to being deployed. So the question is, which transceiver generation is going to be the most cost effective? And the answer goes back to the DSP that we have in each transceiver. Basically, we have on the host side traffic coming into the transceiver, and then on the right-hand side of the DSP, we have traffic going from the DSP to the optics. And as long as we can keep the line rate identical on both sides, we can actually eliminate the gearbox, which is very costly, both in terms of silicon area and cost and also in power. And therefore, we can actually realize that the 800G transceiver, 8 times 100 electrical to 8 times 100 optical and vice versa, is going to be very effective in terms of cost per gigabit. And this is why there's a very strong push in the industry to obtain those 800G transceivers. And again, this is also part of the MASSTART project. So I'll focus now on silicon photonics transceivers, which is the goal of this project. And of course, for silicon photonics design, we need to figure out how to do a laser source, fiber coupling, PAM4 modulation, process with silicon, and of course, develop photodiodes. All of these are difficult tasks, but by far the laser source coupling is the most difficult. And actually, there are many companies doing silicon photonics in the field, actually, except for Intel and to some extent Luxtera. No one is actually selling in volume. And the only reason is being that they don't have a good laser coupling technology. So there are three approaches to laser coupling in silicon photonics. The first one on the left side is the hybrid integration perfected by Intel. Amazing process, but very complex and very costly, unless your name is Intel. On the right hand, in the middle, we have the back coupling approach, where actually you open a cavity in the SOI wafer and you drop the indium phosphide die into this cavity, and you back couple it to the waveguide. And on the right-hand side, we see the optical bench approach, which is actually a free space optical coupling. It may be kind of a brute force approach, but actually it's pretty efficient. So in this project, we were looking for a low-cost design for volume and mass manufacturing of silicon photonics-based transceivers, as was described in previous talks. So we decided to focus on a free space laser coupling, which actually will enable the mass production of those devices. It may not be the best, the most efficient or the most elegant laser coupling technology, but it is definitely the lower cost and simplest one to develop. So as described before, we have here for this project, we are looking into 2 or 3 different demonstrators. The first one, the 400G demonstrator, is based on the DFB laser from Alame. Then we have the PEAK design from Bright Photonics and Leti, which will be described in this conference. And then the packaging is carried out by DustPhotonics, Icontech, and Mellanox. The same goes for the 800, which is a WDF solution. It will not be, of course, a transceiver. It will be more of an optical onboard optical engine. The difference between the two, except for the bandwidth, is that the 400 is a parallel, the DR4 a parallel design, while the 800 is a WDM design. So we have a MUX here, and MUX on the transmit and DMUX on the receive side. For developing the transmit module, we decided to use an optical bench approach where we develop a bench from silicon using standard silicon processing technologies, and we position all of the components on this bench. And again, the laser coupling is a free space. We can see some simulations here below, and the actual design is shown here. So we see the silicon bench, we see the laser from Alame, we see a microlens array, we see an isolator, and some coupling optics that guide the light into the silicon photonics peak. And on the other side, we see an edge coupler, we see a microlens array, and this gray stuff is actually the fiber array. Actually, we are going to DC connector from US Connect. I think we will be one of the first examples of using this very sophisticated and new connector in the industry. Again, the whole idea for this design was to simplify the assembly, to make it as low cost as possible, and to enable automated assembly. Of course, also, we made sure that going from 400 to 800, we use the same technology identically. The only difference is, of course, in the dimension. The silicon bench is slightly larger, and of course, the silicon peak itself is double the capacity. Everything else is identical. Actually, we even use the same microlens arrays for both cases, and here we see a cross-section of one of the benches that came out from the fab. Coupling efficiency is pretty good. We have like a 1 or 1.5 dB, a 2 dB coupling loss simulated. This is not as sufficient as the more sophisticated hybrid or bad coupling, but it should be sufficient as long as you have enough budget in your loss budget. Similarly, for the receive module, we are using the same idea. We have the receive peak, mixed here and parallel here, and just the same fiber array that was used for this task for the transceiver. We are reusing it again to save cost and process, and we couple the light from the fiber array to the silicon photonics peak. Again, this is a standard silicon photonics free space optical coupling. Regarding the assembly itself, again, we are looking for an efficient optical package. So using our collaboration in this project with Photonics, which was described in the first talk by Moritz. So we have, for the entire process is fully automated with minimal labor. So we have standard silicon processing for the bench, and we have, again, die attach for the laser bonding, for the laser. Again, these are standard processes. And then for the next 4 steps, we're actually using the Photonics machine. So this is a fully automated process. Actually, the first 2 steps are fully passive, and only the alignment of the microlens is actively done by the Photonics machine described previously. Similarly, for the receive module, we use only the Photonics machine. There's no need for any previous data or anything. We just position the silicon photonics peak and the fiber arrays and assemble it. So the key takeaways from this talk is that the next generation data center optics, both multimode and single mode, will be used, and strong push to go from 400 to 800 and already to 1.6. Of course, we use this technology also for the 1.6 terabit demonstrator. Silicon photonics has been long regarded as the technology that will reduce the cost associated with the EML-based transceiver, which are more popular today. So far it has not been proven yet, and still silicon photonics is more expensive than discrete EML-based transceivers. So this project is another attempt to bring silicon photonics into high volume manufacturing while maintaining a low cost.